have you draw this, but this was actually on a final before. We gave the 5 dxy order. Okay, so you might want to write that down, 5 dxy. How many nodes are we expecting? 4 nodes. N is 5, there's 4 nodes. How many of those nodes would be angular? Of the 4? 2, because that comes from the smallest energy d orbital, the 3d. There'd be 2 nodes, so the other 2 are radial. This is what it would look like. This is the picture that was given, and there was an angular node here and here, and then 2 radial nodes. This is one way to draw the d orbital. Here's another artistic rendering. So this is the 5 dxy. Here's another way to draw it. This is more actually what it might look like. But I could never imagine having to grade something like this. And we didn't even ask people to draw it, just to identify the total number of nodes and what kind they were. Okay? So I just wanted to show you an example so you can see that. Remember that, and this will be important again in chapter 10, these are out of phase, the different lobes, kind of alternating. And that'll be important in chapter 10, not as much right now. So that's why you see the different colors of red and blue. Not to concern yourself with that too much right now yet. Okay. So thus, with that, if I say draw a 2py orbital, by the exam at least, you should be able to draw that. Or if I said draw a 3d x squared minus y squared orbital, by the exam you should be able to draw something like that. Okay? So the s, the p's, or draw a 3s orbital, you should be able to draw that. Okay, what the heck just happened? And this is in your reader on page 71. In the reader on page 71. The particle in the box in the 3D wave function basically say the electron, according to de Broglie, can be both a particle and a wave. So we're focusing in on the wave part. And the electron, so because it's a wave, we can model it with a function. And in math, you might say f of x or g of x, but we're going to say psi of x, and we're going to call that the wave function. Okay? So the wave function is psi of x, or psi of x, y, and z. Okay? And there's 2 different kinds of wave functions. For the 2D, there's psi of x, and you're not really going to use this formula, but I showed it to you. It's a sine function where you can find lambda, but you should be able to find lambda, you should be able to find n, you should be able to find the number of nodes. And then there's a 3D wave function. This is given by the table in your text, but it's also in your reader. The radial part and the angular part of the wave functions for the 3D. For spherical, the reader also gets Cartesian equations. So we have these functions because we're modeling an electron. These are orbitals. But then you say this is so complex, let's use quantum numbers right now to do, at least for our class, something similar. So it turns out, as these equations are derived, especially the 3D one, that psi of r theta and phi is really psi of NL. NL would be like 1s or 5s or 3dx or 3dxy or 4pz, anything like that. And we know from what I mentioned last time that n represents energy and size. So the larger n gets, the higher the energy. So 2s is higher energy than a 1s orbital. A 3s orbital is higher energy than a 2s orbital. We also know that n represents size, so the bigger n gets, the larger the size. So for example, a 3p orbital is larger than a 2p orbital. We also know that m sub L represents orientation in space and really the number of orbitals. So the number of m sub L values is the number of orbitals. For a p orbital, m sub L would have 3, so thus there's 3 p orbitals. For a d orbital, there would be 5 m sub L values, so there's 5. D orbitals are oriented differently in space. That's kind of the summary of this wave function section that we've just covered. And you'll see if you have the reader, at the end there's a couple overviews of the 3D orbital section that I recommend you look at if you feel a little confused. So a couple 3D orbital, 3D overviews. Overview 1 and 2. Okay? So that's what we've been doing. We've been trying to find functions that model the electron, whether in 2-dimensional space or 3-dimensional space. Okay? And those are what we call orbitals, the S orbital for 3D, S orbital, P orbital, D orbital, etc. There are, I'll just call your attention to it, there are a few things in the some of the videos and some of the older exams that we don't cover in our curriculum anymore. Specifically, those are when you use a wave function to solve for a node, solve for R in a node. We're not going to do that. So if you see anything asking for R in a node, you don't have to worry about it. Okay, there is one more orbital that I want to cover. And this is, one more quantum number to cover. And this is really page 70 and 71 of the textbook, of the reader and the textbook. This is page 282 and 283. The last or fourth of 4 quantum numbers we're going to learn is called the spin quantum number. And this in the textbook in the reader, section 9. Spin quantum number. It's symbolized by m sub s. Some in kind of a Chem 2A sort of class, they describe it as like a globe. So if you imagine a globe spinning on its axis, almost like an electron spinning, and it can spin one direction or it can spin the other direction. Technically, that's not what's happening. It's more due to the curvature and the angular momentum that's causing what we call spin. But this is kind of a way to explain it. Electron can spin one direction or the other. So it's a spin quantum number, and it can be represented a couple different ways. And for this, I'll just show you the reader. Right here on the top of page 71. So if it spins one way or the other, that's an up spin versus a down spin. Okay? Up spin versus a down spin is the word we might say. You can symbolically represent that by an up arrow or a down arrow. So up spin is represented by an up arrow, and a down spin represented by a down arrow. Unlike the other quantum numbers, which seemingly have unlimited numerical values, the spin quantum number only has 2 values. It can either be plus 1/2 or for up spin, or negative 1/2 for down spin. So those are the only 2 possible numbers. And the other thing interesting about this, it is not connected to the other numbers. So for example, you would say, well, L is always 1 less than N. And m sub L is connected to L because it's between plus L and minus L. This one is not any of that. It's its own independent number, and it can be up or down. Okay? So an electron having an up spin or a down spin. Up arrow, down arrow, or plus 1/2, minus 1/2 respectively. That's about it with this one, but this one kind of helps us introduce the next section. So that's all we got on the spin quantum number. We're going to use it in the next section, but in and of itself, that's about it. All right. I kind of like this next really sections 10 through 12. Multi-electron systems. So if you weren't aware, everything we did so far was for one electron. Only one electron all by itself. But as you probably know, elements, compounds have more than one electron. The math can get complicated, but we're going to do kind of an overview of that topic. And this is going to sort of tie together the quantum numbers a little bit better. So let's take a look at the periodic table. Let's see if I have an extra one to show you as well. But if not, you can just look at the periodic table up on the walls. Yeah, I'll show you mine in a little bit after we talk. Well, I guess I can show you now. This one just looks a little scary. There's a lot of stuff on it. Okay, look at this or the ones on the walls, doesn't matter. Okay. So, let's talk about the s orbital. Let me show you this other picture first. We'll start with the s orbital. How many s orbitals are there? How many m-sub-L values would there be for an s orbital? Just one. So there's one s orbital. And it follows a really nice pattern. I'll show you this. This will be a better one to look at. A really nice pattern on the periodic table. The first two columns represent the s orbitals. And you might have done electron configurations in high school. How many have done this before in high school? We do like 1s2, 2s2. Okay, good. Let me explain that a little bit. Then the p orbitals are the right-hand side. We call the p block. Those would be where p orbitals go into an atom. The d orbitals are the transition metals. That's where electrons go into d orbitals. And then the lanthanides and actinides down at the bottom. That's where electrons go into f orbitals. Okay? So, the first two columns represent s orbitals, and here's why. Because there's only one s orbital, it's a sphere. And you can get two electrons in it, an up electron and a down electron. So that's why there's two columns for the s orbital. Because the first one fills up, say, the up spin electron, and the second one tosses in a down spin electron. Let's go over to the p's now. Look at the p's. How many? See, there are 6 columns of the p's. 1, 2, 3, 4, 5, 6, counting over. That's from boron to neon. So how many p orbitals were there earlier when we talked about them? 3, a px, a py, a pz, these p orbitals. Each p orbital can take an up spin and a down spin. So 3 p orbitals taking 2 electrons each gives us 6 columns. That's why in that part of the periodic table there's 6 columns. Okay, let's go to the d's. How many d orbitals are there? There's 5 d orbitals. Here's one of them. Okay, there's one d orbital right there. There's 5 d orbitals. Each one can take 2 electrons, an up spin and a down spin. That's a total of 10. If you look at the periodic table and count the d orbital columns, there's 10 of them. That's why there's 10 there in the transition metal block. It follows this pattern of the quantum numbers. Now for the f's, how many f orbitals are there? Total of 7. Each one of those 7 can hold 2 electrons, an up spin and a down spin. So 7 times 2 is 14. That's why there's 14 columns here in the f block. Okay? So that's why the periodic table might look a little funky, but that's why it's patterned the way it is, because it's filling up certain orbitals until they're maxed out with electrons. It's going to the next orbital. Okay, so how does that work? Probably just like you learned in high school. If you look at the S's right here, the first column is 1s, that's the lowest energy S orbital, 1s, 2s, 3s, all the way down to 7s. So because this is all the elements that are discovered so far, 7 is the last value of n that makes chemical significance. Okay, so from 1 to 7, 7 is the last value of n that makes chemical significance. And that's why F is the last value of L that makes chemical significance. So really 7 chemically is the max for N, and 3 or F is the maximum for L. Okay. So, but for fun, you can think theoretically if you want, like a 8s orbital that was discovered. Okay. Anyways, if you go over to the P's now, notice the P's count start counting at 2 and not 1. Why is that? Yeah. One P orbital is not allowed, because that would mean N and L are equal. So it has to start at 2, that's why it starts counting at 2. Okay. Look over at the D's now. D starts counting at 3 because L is what? What's L for D? 2. So N must start at 3, and that's why the 3D orbital is the first one. Okay? Goes 3, 4, 5, 6, etc. And then the F, same thing. The F starts at 4, because L is 3 for F, and N must be 4 minimum. Be 1 bigger than L. So that's why the periodic table is shaped as it is, and that's how the numbers go. And so we're going to write something out called an electron configuration, which tells us what orbits the electrons go into. And that's helpful for us, because then we can know what electrons are where, and it will ultimately, maybe not right now, but ultimately can tell you something about the chemistry. So let me move this out of the way. I'll get a new slide. So again, it's page 72. I'm kind of going on to page 73 of the reader here. And I'm going to go atoms, an electron configuration, and then there's going to be a mystery column here. I'll fill in just a second. Okay, hydrogen. Let's get this back. A hydrogen, its electron is going to go into the 1s orbital, and so we'll go 1s, and we'll put, it has 1 electron in the 1s, so that superscript represents the number of electrons there. Helium. Also an s orbital, it's going to put a second down spin into that 1s orbital, so it's a 1s2, 2 electrons there. Lithium's the next one, 1s2. Now that's full because the s orbital can only take 2 electrons. Lithium's in the second row, that's why we're going down to the 2s now as the next energy level, and we're going to put 1 electron in the 2s. Remember, 1s is full, it can only take 2 electrons. Then lithium, beryllium. Beryllium is 1s2. Now it's going to put a second electron in the 2s. Now the 2s is full. With beryllium having 2 electrons in the 2s, 2s can't take any more. Now we're going to go to boron. The next one's going to break into the next orbital. 2s2, 2p. If you look at your periodic table, 2p is the next section, and it's a 2p1. You've got the first electron in the p orbitals. Boron, carbon, 1s2, 2s2. Now we've got another electron, 2p2. Carbon, nitrogen, 1s2, 2s2, 2p3. Let's skip ahead to neon, 1s2, 2s2, 2p6. What's the maximum number of electrons in the p orbitals? 6. So now I've got to go on, and that's why you have to go to the next row. Sodium is in somewhere else on the periodic table, in the next row, and it's going to break into now the 3s. So once we go to sodium, 1s2, 2s2, 2p6, 3s1. Okay. And you might be thinking, if you're environmentally conscious, you might be thinking, you're wasting so much ink writing this. That's why we have another column shorthand. Why waste all this ink? What you can do with the shorthand is write the previous noble gas in brackets, neon, and then just write what's after neon. So say basically whatever neon is, and then start at neon. So you can go to the previous noble gas if you want to do a little shorthand notation. Let's see, let's do magnesium. Either would be 1s2, 2s2, 2p6, 3s2, the second electron in that s orbital, or neon 3s2. Either way is okay, the shorthand or the longhand. Let's jump up a little bit. Let's do chlorine. That would be 1s2, 2s2, 2p6, 3s2. Now, with 2 electrons, the s is filled. We're going to go over to the 3p. Aluminum, silicon, phosphorus, sulfur, chlorine. That's 5 columns over. Or you could say neon, 3s2, 3p5. Okay. So you need to get used to doing this such that if I give you any element, you can write either shorthand or longhand, whichever you prefer. Let me show you one reason why this is interesting. If we look at phosphorus, let's do phosphorus for fun. That would be neon, and that's 3s2, 3p1 for phosphorus. 3, it's the third column over. Now let's do arsenic. As. That's neon. Not neon. I'm crazy. What's the previous noble gas for arsenic? Argon. That's 4s2. What's after calcium? What level goes next? 3d. What number takes us up to zinc? 10. And then what's next? What p? 4p, what number? 3. I don't know if you ever heard of the old school way of killing people through arsenic poisoning, but that's when you substitute, put in arsenic, and what that does, look how similar it is here from what I underlined to phosphorus. It'll substitute in your body for phosphorus, and wherever phosphorus is, in some places it substitutes, and it's similar because its electron configuration is similar. However, it's just different enough that it causes issues which could ultimately lead to death. So similar enough to substitute, but not to be chemically identical. And so that's why arsenic poisoning, was a prime way to kill people before, or still causes issues if there's arsenic in the drinking water, because it's substituting for phosphorus in the body. And why is the reason that does that? It's similar. Not only is it in the same column, it has a similar electron configuration, which means it's similar chemically, though not identical. So that's why columns have similar properties, because they have similar, what we call electron configurations, where the electrons are configured in the different orbitals. Okay. So that's just one reason why these electron configurations are interesting. You'll see more as we go into the other chapters. So what I'm going to teach you now is 4 different styles of electron configurations. Number 1. And this is starting on page 73 of the reader of the textbook we're kind of getting on to page 288 or so. So here's the different styles. The first one's the one you already learned, SPDF index. So for example, I'll do this in a different color. For example, carbon is 1s2, 2s2, 2p2. That's an example of SPDF index. And by the way, this process of writing an electron configuration is called the Aufbau process. When we're filling up electrons in the electron configuration to make a 1s2, 2s2, for example, we put in those electrons, we call that the Aufbau process. Okay. It's a filling process of putting electrons into the correct orbit. Okay, that's the SPDF index. Number 2. There's the SPDF expanded. SPDF expanded is the second type. Let's do this for carbon. There's a 1s2, 2s2. Now there's only one type of s orbital, so nothing happens in this case with the s orbital, but something's going to happen with the p orbital. The p orbital, how many are there? How many p orbitals are there? There's 3. The px, the py, the pz. They can each take 2 electrons, that's why it fills up to 6. But there's 3 p orbitals on the 3 different x, y, and z axes. So what you can do instead is to write these separately. 2px, 2py, and 2pz. So instead of writing 2p by itself, you're writing a conglomerate of 2px, 2py, and 2pz. This substitutes for the 2p. You just write them in alphabetical order, x, y, and z. And then what's going to happen is your electrons are going to fill separate ones. 2 in this case. This one will be empty. So they actually fill different orbitals separately. It would be as if you went on some sort of conference and your hotel room had 3 beds and you didn't like anybody in the room. So, you're each going to take a different bed. Okay, so you're going to fill separate beds. Electrons, same thing. They have negative charges. They're not attracted to each other. And so they're going to fill separate spaces. Okay? And so that's why the second one says, okay, I'm going to go over here. If there's a third one, it would go in here. Okay? If there was a fourth one, since there's only 3 orbitals, if there was a fourth one and all beds were full, I don't know what you would do. What would you do? All the beds were full, but you needed a bed. You can't sleep on the floor. You're going to double up, but because you hate that person so much, you don't want to look at their face. So you're going to sleep the other way. Okay? So electrons, if there's an upspin filling a bed, the other one's going to be downspin. Okay, so they're as most opposite of each other as possible. I'm sure you are wondering, oh, does that have a name? Yeah, it has a name in chemistry. That's called the Pauli exclusion principle. Pauli says that if 2 electrons need to occupy the same spot, they're not both going to be upspin. They're going to flip. So one's up and one's down. Another way to say that is no two electrons have identical quantum numbers. That's another chemical way of saying it. No 2 electrons have identical quantum numbers. Or another way to say that, one will be spin up, one will be spin down, but they're in the same spot, in the same order. So for example, these two, one spin up and one spin down. These two also, one spin up, one spin down. Another thing that you just learned is called Hund's rule, Hund, H-U-N-D. And that says, it also is the same process I just explained. If you've got, in this case, 3 beds and 2 electrons, they're going to fill individual beds first before doubling up. So it's not going to be 2px2, and the other 2 beds are empty. They're each going to take a separate, what we call energy level, that is of the same equal energy. So that's Hund's rule. They're going to fill up different orbitals at the same energy first before doubling. All right, I think that's a good space to stop.